So let's start. Can you hear me
Yes,
through the mask?
The speaker can
Okay.
sit down.
So we have the pleasure to have Niklas Beisert today, and he will speak about contractions of integrable theories. No, sorry, integrability algebras and R-matrices.
Yes. Okay, thanks very much, Ivan. So thanks very much for the invitation to this pleasant workshop. Indeed, I will talk about contractions of integrability algebras and R-matrices. This is about work we started some 5 years ago, and also some continuing up with our student Diego Im. Yeah, this relates somewhat more to integrability and more towards algebraic aspects of integrability, that is quantum algebra and R-matrices. But in a nutshell, one could say it's about taking contractions of Lie algebras, such as you start with maybe an orthogonal algebra and contract it to a Euclidean or Poincare type algebra. But apply that to integrability and R-matrices. But I wanted to start with a motivation of why I would be interested in it, and this relates back to the ADS CFT correspondence and a certain integrable structure that was found there in the planar limit. I will not go through all of that, but mainly focus on the S matrix, which is an R matrix in the algebra setting. But maybe just illustrate some features of it. So here you have a two-dimensional world sheet, and you have excitations on it. These carry a momentum, and they can scatter. If they scatter, well, there would be two excitations with momentum P1 and P2. This scattering is elastic and eventually totally factorized. And what's important is that here you have 16 types of excitations above the vacuum. 8 of them are bosons, 8 of them are fermions, as you would want for a proper string theory, perhaps. And well, these excitations are sometimes also called magnons. And there's a lot of symmetry in the problem. The string theory and the gauge theory both have PSU 2,2/4 supersymmetry, which is quite a bit. But on this vacuum state or ground state on which these excitations move about, the symmetry is broken to 2 copies of PSU 2/2. And then the excitations transform in a fundamental of each of these PSU. Bosons and fermions, which makes 8 + 8 bosons and fermions. And so you could view these excitations in this matrix form, where you have a PSU 2/2 acting on the rows and on the columns. And in some sense, 4 of these, 4 bosonic of them are related to the ADS5 space, 4 of them are related to the S5 space, and the remaining 8 are fermions, and they mix sort of between those two parts. Well, the overall scattering matrix here has also a factorized form in terms of algebra. So there would be 2 copies of an R matrix which act both on the rows and on the columns. And in addition, there might be some scalar phase that is also an interesting function. Yeah, that much just for the setup. And this R matrix that you find here is quite remarkable. So let me list a few of its features. So it's an R matrix for 2 + 2 particle flavors. So 2 bosons and 2 fermions. These 2 both transform in SU2s in a spin doublet of SU2. So eventually, all of this talk will be mostly in SU2, which is convenient. So all of this talk will be SU2 and maybe a bit of supersymmetry added to it. If you just look at each SU2 part, the R matrix looks much like a rational XXX type 6 vertex with full symmetry R matrix. But if you look at the overall 4x4 R matrix, this is not a plane. I mean, it's not a plane PSU2/2 R matrix if you would just take the standard extension from GL2 to GLN. In particular, it's not of a difference form, so you cannot write the R matrix, which is a function of the two momenta, as a function of a single combination of the two momenta. But the two momenta really enter independently, so you could say it's not of. I should put a minus here. It's not a function of the difference, or maybe the quotient of two other functions. In particular, if you look at the functional dependence on these momenta, or maybe some function of the momenta, it looks like it's actually an elliptic function that is needed. So this again points more towards 8 vertex or XYZ type models. Furthermore, there is some sort of off-diagonal scattering. So I've tried to show this in this matrix form or in this table form. If phi are the bosons and psi are the fermions, then you can, for two particle states, you can build either two bosons, a mixed one, or two fermions. And as usual in an XXX or 6 vertex type rational or trigonometric setup, you would find sort of a diagonal part here, a mixing between those two permutations. And again, two fermions would map into two fermions. That is also the usual thing you would find for supersymmetries GLN/M in the fundamental representation. However, here there is something interesting going on, because there are additional contributions where you map two bosons into two fermions, which by statistics certainly is possible. And also, if you look at the spin, this is interestingly, it is also possible, because these are all spin 1/2 particles, but of different types. So if you take two of these bosons, you would either get a spin 0 or spin 1 state. And also for the two fermions, if you put them together, you find a spin 0 or spin 1, but of a different SU2. But since you do find two singlets, they can mix with each other, of course, and that's where these two contributions are possible, and at least by elementary spin considerations, and they do happen. So you have mixing, you have this sort of off-diagonal, off-block diagonal type of mixing here. And it turns out that this R matrix is actually equivalent to Shastri's R matrix for the 1D Hubbard model, maybe up to some elementary twists, but it can be related. So this is also a well-known R matrix, which is quite complicated and has many different matrix elements that are not so easy to digest. So altogether, the question is, what is the quantum algebra origin of this R matrix? Why? How can we construct it? Why does it exist in the first place? What is the symmetry? How does one get there? Except by just constructing it, but we would like to understand the reason for it. Yeah, I mean, what I'm referring to is that for semi-simple Lie algebras, you can build quantum affine algebras, you can build Youngians, and R matrices for all of these are in principle known, or you know how to construct them. You know how the phases can be constructed. And this somehow doesn't fit that scheme. So the question is, why does it not fit, or how does it fit it, and why do you get a non-difference form? Can it be related? And I'm going to argue that by some sequence of deformations and constructions, you can get there. Yeah, let's talk a bit about the symmetry for this R matrix. So this R matrix was in fact constructed using this PSU2/2 symmetry, but using some unconventional features which are somewhat specific to this particular superalgebra. Well, just as a reminder, this PSU2/2 can be understood as a supermatrix algebra. So you have a 2/2 by 2/2 supermatrix. There are basically in this upper and lower corner, there are two SU2 parts. And then there are supersymmetries on the off-diagonal parts. I'll call them J1 and J2 for the SU2s, and Q bar for the supercharges. And one could say that these are 4x4, 2x2 matrices each, so they are in the spin 1/2 representation of these SU2s. The interesting part here is that you can introduce three central elements. For GLN/N, you find a central element if you do the anticommutator of the supercharges of the Q with the conjugate Q. You find the SU2s, or the GLN and GLN, but you also find as a unit element sort of something which you might call the energy. And that is a central charge. It's a singlet scalar charge. But in addition, here you can also take the anticommutator of alike supercharges and form a singlet element, and you can do this for Q and Q bar, and these are two additional central elements which I'll call C and C bar. They are quite specific to this PSU2/2. Yeah. But the point is, we have now three spin 0 elements in the algebra, and they also take a curious form as they all, the dependence on the momenta of these particles, if you apply it to the particles, is fixed, so it has some curious form here. In addition, also some derivation element was discovered for the algebra. Derivation would be something that acts on all of these generators and maps them to themselves by commutators. In particular, this derivation acts just on the supercharges. So B with Q ordinarily gives you plus Q, and B with Q bar would give you minus Q. This is some charge type operator. Except that here you can do something funny. You can also put Q bar and Q into these relations with some coefficients. And I just want to point out that the presence of these additional elements here somehow relates, I would argue, to this off-diagonal scattering. It's you have all of these off-diagonal pieces also in the algebra, and they should really work one-to-one. So I'm going to focus mostly on these extensions, namely these central elements and some derivation element. And in our work of 5 years ago, we related this to a superalgebra, somewhat exceptional superalgebra D21 alpha or D21 epsilon, where epsilon is meant to be going to 0. And in fact, this PSU2/2 can be obtained from D21 epsilon or alpha by sending epsilon to 0. And yeah, I mean, maybe just as a reminder, D21 epsilon in terms of a vector space is 2 copies of SU2, and three copies of SU2 basically, and 8 supersymmetry generators. But if you send epsilon to 0, something funny happens to one of these SU2s. I'll call it SL2. I don't really make a distinction between real and, I will complexify everything, so there's no difference here. But this SL2 ordinarily would turn into a into just a trivial Lie algebra C3 if you send epsilon to 0. But if you send epsilon to 0 in a slightly different way by doing different types of rescalings, you might actually also preserve the SL2. So there are two ways, two limits you can do here. One is where you get 3 additional central charges, which are just like those that I described here. Or you can have an SL2 derivation, which acts on Q and Q bar as a doublet, which rotates those two into each other. And these are the two things you can get, but you don't get both at the same time. And interestingly, here you do have parts of both. So how does one get it? Well, you can have a Lie algebra with both of them in place. It's just not obtained from D21 epsilon, but you need another copy of SL2, and you just have to have enough elements to get there, right? So if you take SL2 and D21 epsilon and send epsilon to 0 and do a specific contraction, where you combine the generators of this SL2 with that SL2 in a specific way, you can obtain an SL2 and a C3 at the same time. And the PSU2/2 sits somewhere in the middle. And that's sort of the setup that might carry this structure. So I'll call again PSU2/2. The generators would be J1, J2, and Q bar. And this SL2 I will call L for sort of Lorentz, 3-dimensional Lorentz generators, and this is a momentum type generator. They commute with each other, and altogether the algebra structure is listed here. So L with L gives you L, it's this proper SL2. L with P is P. So L and P with P commutes. So this part here is a Poincare algebra. It's a 3D Poincare or 3D Euclidean algebra. And the interesting part is that the PSU2/2 sits somewhere in the middle and transforms under it and generates these momenta. So Q with Q gives you P, it gives you the P's as I described. So one can say this contraction limit of this algebra here gives you 3D Poincare with an injected supersymmetry extension. This is, I guess, sometimes called in the CFT framework also called large n equals 4, if I'm not mistaken. Anyway. But there's also a simplified algebra contraction if we don't want to deal with supersymmetry, which is just if you take SO4, which is 2 copies of SU2 or SL2, and you contract that to SL2 cross C3, which is 3D Poincare or 3D Euclidean. So what I'm saying is we can just drop this supersymmetry. We don't have to deal with it. We can just work with a simplified setup where we just look at that. And the nice thing is that at the end of the day, we can also put this back, the supersymmetry back into place. So we don't have to deal with it in the intermediate stages and just explore what happens with this algebra. Yeah. This looks like space-time supersymmetry. Yes, it does. Yes, it's a slightly funny space-time supersymmetry in the sense that there's something that shouldn't quite happen, right? It is this part here. Q with Q bar normally would give you just the momenta. But Q with Q bar also gives you the SU2 rotations that act on these 2 flavors of on these 4 or 8 flavors of supersymmetry. But this is something specific in 3D, which you can have. It's also listed, I think, in NAM's classification as it's a somewhat special case. It's not the plain supersymmetry algebra in D dimensions. But it's in that sense it's slightly similar to a superconformal algebra as well. But it's space-time, it's just supersymmetry, yes. Well, I mean, the PSU is just reducing it to its elementary pieces, and this SL2 cross C3 is almost, I mean, if you just had a GL1 cross a C1, then it would be U or GL2/2. But here you can do more of an extension, and that's why I just reduced this to the elementary parts. Yeah. But indeed, there are central extensions, there are derivations to it, and those are explicit, and those are the ones that I care about. Yeah, right. Yeah, as I should say, there's actually a further reduction that we need by reducing it to sort of a 2D setting. So we well, not quite, but we can reduce SL2 to a GL1 and C3 to a complex algebra. And that's something we will also need in the end. And if we do this in the supersymmetry setup, we will indeed obtain this GL2/2, except that it's not the standard GL2/2, but some curious deformation of it. Hope I'll get there. So okay, let me get to the actual construction of SL2s. So SL2, I will just call the generators. Just let me name some conventions. The generators will be J0, J plus, J minus. I will always complexify, so don't really care about reality conditions. The Lie brackets, yeah, are of this form with some choices of plus and minus and twos that are listed here. There is a quadratic invariant, of course, which takes this form here, and we also have a bialgebra structure, which is obtained from the classical limit of UQSL2, where the R matrix is this diagonal part and plus and minus, J plus and J minus in one particular ordering. And that leads you to co-brackets, co-algebra. J0 has trivial co-algebra, J plus minus has this J0 with J plus minus co-algebra. These are the things that I will need. So let's consider the 3D Poincare algebra as a contraction. The point here being that Poincare, of course, is not a simple algebra. But you can obtain it from a simple algebra via contractions. And we know the integrability or quantum algebra structures for the simple or semi-simple algebras, and you can then perform the limits on those to obtain something for this 3D Poincare. So we know the isometry algebra SO4 here. Yeah, well, I mean, this contraction can also be viewed as a flat space limit, which is R3, where you take a S3 or ADS3 and take the zero curvature limit of that. You basically focus on maybe the north pole of an S3, and then space becomes totally flat, and the algebra will be Poincare. And that's how you can understand this contraction, because the isometry algebra of the sphere would be SO4, and that contracts through Euclidean algebra in the vicinity of the north pole. In terms of algebra, you could say this is a contraction SL2 cross SL2 going to SL2 with 3 momentum generators, which are transformed by this SL2. And the contraction works as follows. So you take these 2 generators M1 and M2, and you scale them by a factor of 1 over epsilon, but you make it in such a way that the sum of the 2 will be finite, sort of, and yeah, one of them will be this. I mean, both of them, in that sense, this is a combination that's singular in the limit epsilon going to 0. Both of these generators are considered to be singular, but the sum of the 2 is going to be finite, and that's how you get a contraction. So this mapping between M1 and M2 and L and P is completely regular as long as epsilon is finite, but it becomes singular when epsilon goes to 0. So you can take this normal algebra, which is SL2 cross SL2 here, and rewrite it in these new generators, L gives you just the SL2 algebra back. L with P gives you back P right away, and P with P does not give you quite 0, but it gives you something that is of order epsilon in this limit. And then you perform the limit, and that's how you define the contraction, and you obtain a Poincare or Euclidean algebra. Now we can do this, you can apply this to the co-algebra as well, and to the classical R-matrix. So the R-matrix here is, if you just substitute these new generators, is again the diagonal and the plus minus part here, but there's a 1 over epsilon because of this identification here for the R1 part. It's also for the R2 part is 1 over epsilon squared. So what you would have to do is you would have to rescale R1 and R2 by epsilon squared, and you'll end up with something that is of this form. But these are somewhat boring. These are just the P generators. This is just some momentum part. And you can do something more interesting by combining these two R matrices. You can combine them because they are two, these are two simple algebras, and you can take any linear combination of these R matrices to define the overall R matrix. And if we take the difference, you see here, these two have the same leading singularity. You can take the difference of those two to remove that part, and then you can proceed to the next order. And the next order is slightly more interesting because it has some of these L generators, these rotation generators in it. You can even do something interesting, more interesting, by putting another epsilon squared of this R1 part, so this singular part, you can also add it in, and then you'll end up with this R matrix. And that's an R matrix which then satisfies the classical Yang-Baxter equation, and it even obeys it for arbitrary parameter psi, which is this additional parameter. So in fact, you have two independent parameters to define this R matrix. One is the overall factor, which you normally drop, and the other one is just this psi. And the counting is the same as for SL2 cross SL2. You just have two overall factors for SL2s, but here you have one overall factor and this psi parameter. Co-brackets take this form, gives you some interesting structure. L goes to L wedge P, and also P wedge P with this psi parameter, and P goes to P wedge P. So this is in fact something that you can interpret as the classical limit of kappa deformed Poincare. And you can also do this in the quantum algebra setting, in the full quantum algebra setting. So here you would have to take UQSL2 cross UQSL2. But in fact, this prefactor here of the R matrix sort of enters as the Q parameter. And so in fact, this would be U epsilon SL2 cross U epsilon tilde SL2. Where epsilon tilde is related to epsilon, it needs to be the negative of epsilon for this cancellation here to happen. And then you can do a slight deviation from that and introduce the psi parameter. So you would have to take two Q's that simultaneously go to one from above, one from below, and but they don't have to approach it exactly the same. Just the leading order approach has to be the same. And then you can perform this contraction, and both the algebra and co-algebra can be contracted, and that gives you what is also known as kappa deformed Poincare, where you also have this additional deformation from the psi parameter. It's kappa deformed Poincare in 3 dimensions. But nicely, you can also obtain a universal R matrix for this system, where you would start with the SL2 R matrix, universal R matrix. This has some Q exponential structure of the plus minus part and some straight exponential of the diagonal part here. You take 2 copies of those and combine them as before, and The problem here is that then if you send epsilon to 0, you obtain some singular behavior in two of these factors, and you would need to just cancel this singular behavior and see what remains. But the nice thing is that this cancels nicely if you take this assumption here, and what remains is then well, some normal diagonal part in the end, and then there is a curious structure which is something like log 1 minus x over x in the exponent. It's some combination of the generators that remains, but it can be expressed using usual functions like log. But it's not just e to the log, but it's e to the log 1 minus x over x, like some other generators, which perhaps has a funny structure. But maybe even more curiously, this psi parameter also enters just with a momentum-dependent part, and here you find a dialog and another log, which has again adds a bit of funny structure to it. One could also say, I think this Q exponential is also a bit like an exponent of a Q dialog, or at least has some dialog features, so it's not too surprising that you find a dialog in the end, but only for the psi parameter, and what remains here has no dialogues left. What is maybe interesting to see is that the factorization is lost. So before you had two R-matrices of two factors of these SL2s, and you put them together, but they completely factorized. But now you perform the contraction limit, these two R-matrices have to combine so that the divergence is removed. But once you remove the divergence, these two R-matrices are not separate anymore. You cannot disentangle them. So that's how you can actually link two simple Lie algebra structures into this one contraction. And also, I should say, one can supersymmetrize this quantum result here. One can stick in factors for the supersymmetry, but I'm not going to display them here. But I think this is an interesting structure in itself. You could even interpret this as a 3D scattering problem where you have particles with momenta. So the momenta of the particles would enter as this vector p plus minus and p0. These are some massive particles, arbitrary masses, some representations of this kappa deformed Poincare. And the point being is that this R matrix could serve as a scattering matrix which would somehow deform the momenta when the particles move through each other, and the deformation goes through these rotation generators. So it's the resulting momentum configuration is a function of the initial one and perhaps a specific one because it comes from this integrable R matrix. What's this about? Now I want to focus on further reduction of this 3+3 dimensional algebra to a 1+1 dimensional algebra, which is something that we need for this supersymmetric setup. So instead of having 3 L plus 3 momentum generators, we just want to have 1 L and 1 P. In fact, this will be a bit boring because the resulting algebra will be abelian and the co-algebra will be trivial and the R matrix will just be L cross P. But it's an interesting reduction because the R matrix and the bialgebra structure reduces in a somewhat nice way, and in particular because we can extend this to PSU2/2, and it then gives us a somewhat non-standard form of this PSU or GL2/2 algebra, where you have a GL1 and a C factor, but they don't appear in the usual places. So it's a bit interesting to do this reduction, and we will need this reduction for this ADS-CFTS matrix. The first step here So let me just guide you through this reduction, and maybe you could, if you also have an idea what this reduction is or how you can interpret in an algebraic sense, I would be curious to learn or discuss with you. So the first step is you twist the R matrix, you twist the co-algebra, you add a diagonal L wedge P term, which is something that you can do. So the R matrix gets a bit twisted. It's a valid twist because L0 and P0 both have trivial co-bracket, and they also commute with each other. And so this is sort of a twisted co-algebra, which you need, which you can do simply. But it allows you to do something interesting then. So we can now define in the second step a subalgebra of the SL2. So of course SL2 has different types of subalgebras. You could take L0 with L plus or just L0. Here I want to take L0 and L plus with a specific combination. So this is a one-dimensional subalgebra, which is not too exciting by itself. But there's still the momentum part. So we can look at what the algebra structure is when you act on the three momenta, and you find the result can only be a combination of P plus and a certain combination of P minus and P naught. So what it means is that there is a two-dimensional ideal spanned by P plus and by this generator. And we can of course divide out this ideal. So dividing out the ideal will also reduce the momenta from 3 dimensions to 1 dimension. But it's not a subalgebra, it's an ideal here. So that's the next thing. So first I did here, I took a 1D subalgebra of SL2. Now I do a 1D, well, I reduce the two-dimensional ideal, so I reduce the 3 momenta to 1. And yeah, when I divide out this ideal, I would just set P plus to 0, I would set P naught to P by definition, and I set P minus to something that's also proportional to P. And the resulting algebra will be L commutes with P, not too surprisingly, because I set both of these combinations to 0. But the interesting part is I can apply this to the R matrix, and then I get R is L cross P and P cross P, and you can see this as follows. If I just do this. If I just rewrite the original R matrix that I had here after the twist, this one, I can rewrite it in terms of the new generators. I can say, well, there is a part which is just the new subalgebra generator times P naught. And then there are some parts which I can write as ideal generators, but these ideal generators are set to 0. And that's nice because they multiply something that is not part of the subalgebra. So it reduces away those parts of the algebra that shouldn't be there in the final algebra. It's sort of I remove this part, and the unwanted parts go away, and what remains is just something that can be expressed in terms of the new simpler algebra, just L cross P and P cross P. But the nice thing is that the classical Young-Baxter equation follows because of this funny structure here. This is actually very similar to the BRST reduction of in gauge theories, where you have some things which are which are closed and exact, and you could divide out the unphysical degrees of freedom. And so whether you work with the S matrix in the full model or after reducing out the unwanted degrees of freedom doesn't actually matter. Unitarity, for example, holds in both cases. And the same happens here. The classical Young-Baxter equation follows because of this particular combination of taking a subalgebra and dividing out an ideal. Yeah, but also, of course, you can supersymmetrize this, and so then it becomes more interesting if you stick in the supersymmetry generators here, and you obtain an interesting sort of R matrix, and the algebra is somehow intertwined in a non-standard way. In our work, we wanted to lift this towards the ADSC matrix that involves quite a few steps. As I said, first you can extend to supersymmetry. This is something that takes a bit of patience, but works straightforwardly. But here we've just worked in the finite Lie algebra setup. We should actually extend this to a loop or affine algebra. And you can do this either with a rational or trigonometric setting. We should lift this to quantum algebra or quantum affine algebras. We can simplifies the setting a bit. And note here that we are dealing with Poincare representations. We should be dealing with our space representations as usual. So these are infinite dimensional representations, and that also makes things a bit difficult. And this reduction that I just pointed out here can be applied to the loop algebra settings as well, and maybe that helps us a bit understand why we have this, what this three-dimensional structure behind the ADS-CFT S matrix is all about. So by putting all these steps together, I expect that we find the worldsheet S matrix and corresponding quantum algebra for this as a sequence of contractions and reductions of quantum affine algebras, D2 epsilon, of this D2 epsilon algebra. We understand the affine structures and maybe also a Lorentz boost. What is the meaning of the Lorentz boost in the quantum affine algebra for ADS-CFT? Yeah, and that I already mentioned. And I think as a final slide, I can just show you what happens to the reduction in the Poincare loop algebra setting. So if you apply this now to a loop algebra, we have a rational twisted R matrix in this Poincare algebra. This is again L cross P and P cross L divided by U1 minus U2. These are the spectral parameters, and you can also have a Xi parameter. And we want to apply a twist. It's just a certain combination that can be done. And for the subalgebra, we take of the Lorentz algebra, we take L to be the diagonal part, and the the L plus and L minus generators are also added, but with something that depends on this spectral parameter or this loop counting parameter. So this is not homogeneous in loop level. We take a combination of a generator which is in the diagonal part of some loop level and in the off-diagonal parts shifted by one loop level. It's something that you can do because you can treat U mostly as a parameter. But that also, you can still do the ideal. You still have an ideal, but the ideal again depends on this loop level parameter, especially for the P plus minus parts. And then you substitute this into the R matrix, and because of the structure, again, the Young-Wechsler equation follows. That's very nice. But the R matrix now becomes, if you rearrange the U dependence, something like this, and it's the usual rational R matrix structure, but here you find additional factors of U1 and U2, which are somewhat curious that these are here. So you have some extra dependence on the loop level due to this curious reduction. And I should point out that this is not of a difference form, so you get some of these non-difference form structure through the reduction. You can also do this for the trigonometric R matrix. It's slightly more complicated, but in structure, it's sort of the same picture you get. And you can also supersymmetrize that, and you should also be able to quantize that. And that, if you put everything together, I think you will get to the ADS-CFT R matrix in this way. Yeah, so thanks for your attention, and that's the end.
Questions?
I'm not sure if I need the microphone, maybe for the people out
Can you
from
turn
outside.
it on? Is it on?
On?
Yeah.
Is it on? Yes. Okay. So in my understanding, the goal would rather be something more abstract, not finding the R matrix itself, but the universal R matrix, say, underlying this R matrix. So for me, one of the, say, amazing things about this Shastri R matrix, as I call it, is that it's not embedded in a family. I mean, there is not something which looks like coming from representation theory, and you would want to have a universal R matrix structure where you can, applying representation theory, you can get all families associated with all finite dimensional representations. You would be wanting to construct Q operators and so on in a representation theoretic setting. Are you expecting to get into that direction, to some universal R matrix structure?
Yeah, I mean, this should, if you can perform the whole, if you can perform the whole in practice, then this would lead you definitely to the universal R matrix that also applies to, I mean, would give you Shastri's R matrix as a particular representation. This is not necessarily a very, I mean, it's a rather singular representation again. So some of the structure or some of the complicated structure actually simplifies a lot in Shastri's R matrix. But yeah, in principle, all of this, I mean, this would give you a universal setting. I don't know if it's very useful. I'm not sure you can learn too much for concrete applications in the 1D Hubbard model, and several things just because you're looking at a very particular point within this universal setting. It might be easier to do many things just without this framework. But in principle, yeah, one thing is that you would obtain the structure, and the other thing is that maybe one can learn a bit about what these reductions or how these reductions can be applied, how contractions can be applied to other algebras, and maybe that gives you some interesting quantum algebra structures for non-simple simple Lie algebras.
I have a naive question, perhaps related to the last one. You know the quantum spectral curve of the PS224 algebra. Can you say something following your construction for the spectral curves of the reductions, of the contractions?
That will also be interesting. How if you understand this algebra, how this algebra might fit into a bigger PSU 2,2/4 algebra. Yeah, that would be interesting to see. But you certainly need some extension of PSU 2,2/4 that would also incorporate these additional structures that I find here. But yeah, I don't know about quantum spectral curve, how that fits into the picture, but this certainly addresses some relevant structures of it. Yeah.
Thanks. No more questions? So let's thank Niklas again.